All right, so in the emails, I think the last 2 emails, both of them, I've had the lecture video. So you can go back and watch it, or if you're not here, you can go back and watch it. This materials, it's not easy. But, so last week we talked about the redox reaction. The redox reaction is that transfer of electrons. One molecule or atom wants to give up the electrons, the other one wants to receive it. The oxidized one is losing the electrons, and the reduced one is gaining it. And we see that as the reduction in the oxidative state going down. So that oxidation state was what the metals, the individual atoms' charge were if they are separated. So if we had hydrogen chloride, we separated the hydrogen from the chloride, hydrochloric acid. That hydrogen would have a +1 charge, and the chlorine would have a -1 charge, and that's their oxidative state. All right, so metals we saw were good donors of electrons, while the transitions metals would have that sea of electrons, and that's what contributed to the properties of metals being good conductors or shiny, malleable, or ductile. So non-metals were good at receiving the electrons. Those were the ones that were reduced because they went down in their oxidative state number. They became lower, reducing. We talked about batteries. And conductive wires, how they employed those characteristics. So one thing that is in a battery is the electrolytes. So your lab report was due today. I'm happy to give you feedback and allowed you to rework it. I want to look at some people's lab reports to see what they did. And I encourage you to incorporate some of the feedback I give you off the lab reports I pull off, and make changes and resubmit it next week. Because there's no way for you to learn how to do it without me saying, change it here, add this. That graphing, I wouldn't have learned that until college, adding the R squared and displaying the equation. But that's what we call a mathematical model. That's how you can use the data you get to predict situations you didn't test for. All right, so we're going to move on to acids and bases. So just like how a redox reaction exchange electrons, acid and base reactions exchange protons. So our hydrogen atom likes to lose its 1 electron. Can you all recall what the electron configuration for a hydrogen atom was? What was its principal quantum number? Yeah, hydrogen. 1. Principal quantum number of 1. It only has 1 orbital. What's the letter associated with that orbital? What do we call it? S. And it only has 1. And this 1 S orbital it's only half full. It's happy to give it up. Our hydrogen is happy to give up its 1 little electron and go from its ground state of 0 to a +1 charge. Now, we call it a hydrogen atom with a positive charge, but it is a proton. It's just 1 proton without any electrons to balance it out. So every time you see an H+, you can think of it as a hydrogen atom, or you can think of it as a single proton. So acids are molecules that readily donate hydrogen ions. So bases are molecules that readily accept those hydrogen ions. So we talk about water a lot. Water is hydrogen plus hydroxide will become water. And water makes up most of the things we deal with in our world. So water is half hydrogen, half hydroxide. Those come together to make the water atom. The hydrogen, so the book, I felt like it made it sound like anything with a hydroxide ion is a base. So there's a couple definitions for acids and bases, and it's kind of evolved throughout history. So at one point they said anything, I think they still say anything that donates a hydrogen is an acid. It can be a strong acid, it can be a weak acid. We covered both of those in your reading last week. If it has a hydroxide ion, it will accept a hydrogen. But a hydroxide ion isn't the only definition of what makes a base. If it accepts a hydrogen, even if it is not a hydroxide ion, it still is a base. So an example of that is ammonia. Ammonia is NH3. it will accept a hydrogen ion and become NH4, which is ammonium. It's not a super stable molecule, but it does exist. So even though ammonia does not have a hydroxide ion component, functional group, it still is a base. Riveting, huh? I'd like to leave this open because it's hot, but not with the vacuuming. Can y'all hear well? Okay, we'll see. All right, so some common acids. So hydrochloric, that is a strong acid, readily dissociates. Acetic acid. Anyone know where we might find acetic acid? What? Oh, not lemons, close. Vinegar, yes, vinegar is acetic acid. Sulfuric acid. Yeah, I don't really keep sulfuric acid in the house. Carboxylic acid. So I've denoted this here with an R, a CO2H. So when we move into organic chemistry, anytime I have a carbon chain, which most organic molecules are made up of series, it could be 1, it could be 50 carbon molecules. If I'm not being clear about what type of organic molecule I'm talking about, I'll just put an R, and it could be any old carbon collection. So a carboxylic acid will have this functional group at the end. Citric acid, there you go. It is the acid of fruit. And lactic acid. So lactic acid is common in kombucha or any sort of beer, any sort of fermentation. Sourdough breads will have a variety of acids, including lactic acid, and also exercise. The burning that makes you quit exercising because your muscles hurt so bad is your body making lactic acid. So strong acids readily dissociate and release all their hydrogen ions. All right, so common bases. Ammonia. Where do you find ammonia? Yes, you can use it as a glass cleaner. A lot of glass cleaners are non-ammonia. Where if you're not buying like chemical ammonia in the grocery store. How about a diaper? Like pee? It's pee. Your body excretes a lot of ammonia. Sodium bicarbonate. It's baking soda. So I mentioned bicarbonate on the other well. All right, calcium carbonate. So this is what is in hard water. Eggshells. It's a natural base. We're going to come back to carbonates. Strong bases disassociate and release all their hydrogen ions or attract. They either disassociate and release their hydroxide ions or attract hydrogen ions and absorb those. All right, so to study pH, we have to understand a little bit about logs. How many of you have studied logs? I don't know if that's Algebra 1, Algebra 2. Anyone have a clue? Where did you learn about logs?
Algebra 2.
Algebra 2? All right, we're going to learn about logs right now. All right, so if I had 5 to the power of 4, that would be 5 times 5 times 5 times 5. So 5 times 5 is 25. 5 more is 125. And fortunately, like I did it on a calculator, it's 625. So the way a log function works is I take the number that I'm raising to a certain power, put in parentheses what that answer is going to be of it raised to a power, and that equals the power it was raised to. So 5 to the power of 4 equals 625. So 2 to the power of 6 equals 64. So log base 2, 64. How many times did 2 have to be raised to a power to get to 64? 6 times. So that is the answer to my log function. pH is measured in a base 10 scale. So in my 2 examples, we have a base 5 and a base 2. Logs can be written to any base. If you have a natural log, it's written to a base E, which is a number that's kind of like pi. It's just this number that we see in nature. It's just a fixed value, kind of like a mole. But logs are a base 10 scale. Our number that we're taking a log of is the hydrogen ion concentration. It is a very small number. If you recall, when we had moles, we tend to have a small number of a hydrogen. A mole is a large number, but the concentration in our solution tends to be a small number, and it's a negative log. So because this number is so tiny, we make it negative. It's because the concentrations are expressed as a 1 times 10 to the negative power. So each whole pH unit represents 10 less than the previous. So because it's negative, as a concentration goes up, the answer will go down. Yes. So the more hydrogen there is in a solution, the more concentrated the acid is, the lower the pH will be because of the negative in front. So here's the equation for you to remember. Write it again. All right, so an example. Negative log of the pH of a hydrogen ion concentration. This is in square brackets because that denotes concentration. We'll give your pH. So if my concentration says 0.0001, I'm going to change that to scientific notation. 1 times 10 to the negative 4. So I'm moving my decimal place. 1, 2, 3, 4. So I start with a small number. It gives me 1 times 10 to the negative 4. I take the negative 10 log of that. That is going to give me a pH of 4. So this is a calculator function. You'll get your concentration. You'll hit log. It'll give you a number. You change that negative number to a positive. And that is going to give you your pH. How'd y'all feel about that? All right, so here's one. 0.001. It's move the decimal point 1, 2, 3 decimal places, so it becomes 1 times 10 to the negative 3. Log base 10 of 10 to the negative 3 will be negative 3. But I'm going to convert it to, I'm going to apply the negative so it becomes a positive number. So the pH will be 3 when we have a molar concentration of 0.001 moles of hydrogen per liter. Yeah.
The book did also say that whatever exponent was on the number was the pH.
That's, yep.
So if it's a non-decimal number, then it's easily calculatable.
The tens cancel
you don't
out
have to use the log
because it's a base 10. But I'm going to give you ones that are not, that do not cleanly cancel out, that'll have a decimal. So you'll have to use your log function. But yeah, you can see the tens cancel out because it's 10 to the power of 10 to the power of something. All right, so how to solve a log function? Log base b. So that is your base, be it 2, 10 in pH. It's always base 10, but it could be anything. Of x equals y. You just rearrange it. So for example, log base 2 of 8 will equal 3 because 2 to the power of 3 is 8. Log base 10 of 100 is 2 because 10 to the power of 2 is 100. Cool? All right. So whenever that you don't see a base number, it's because it's to the power of 10. It's just implied. And these brackets here are what means concentration. So as we go forward to our K, our equilibrium constants, Kw, KOH, Ka, we'll continue to see these brackets telling us that it's concentration. All right, some examples. All right, if a solution has a pH of 2, how many moles per liter of hydrogen ions? Do I answer it? So, negative log of a pH concentration. It equals 2. Ten to the negative 2 is 1. What am I doing here? So rearranging it, so it's 10 to the negative 2. All right, if a solution has a pH of 7, how many moles per liter? So I solve that by going log, well, starting with my base equation, log concentration of hydrogen ion equals 7. 10 to the power of negative 7 is this. Is that number. Take a minute and study that. Make sure it's making sense to you. See if you could figure that out on your own. So I'd like to break out your calculators, your phones. See that you know how to work it, because you often have to put the number in and then change it to a negative number on an iPhone. I understand. I'm sorry. Can you guys read this? Move closer. So it says if a solution has a concentration of 1 times 10 to the negative 5 moles per liter, what will be the pH? So I'm either going to give you the concentration of the hydrogen ion, and you're going to take the log, or I'm going to give you the pH, and you're going to have to tell me the concentration of hydrogen ions by taking the anti-log. So when given the pH, it tells me I need to move the decimal point that way, to the left.
Wait, so what are we supposed to
So seeing that you understand why, if the pH is 7, what would the concentration of it be? These are two separate problems.
Oh, okay, so are we doing this? I'm confused. As to
Okay. So I'm telling you here, I want you to understand that if I gave you a pH of 7, I want you to back calculate what this concentration of hydrogen ions would be. So by raising it to the power of 10. So if my equation told me over here, how did I arrange it? That if my concentration is Y, or my pH is Y, if I take 10 to the power of Y, it's going to give me my hydrogen ion concentration.
like, I'm so confused.
All right, so let me do it here.
Can you write it?
Yes. All right, my equation is log 10 of my hydrogen ion concentration equals pH. It's negative. All right, so in this first one, I'm saying my pH is 2. So I rearranged this equation. Go back this way.
But didn't you just put the answer?
I did. The answer is there. I want you to.
So that's how I was
yeah,
confused, because I was
I'm
like,
giving
that
you the
makes sense.
answers.
I thought we were supposed to find something else.
No.
Okay. Well, now,
So 10, the base, to the power of Y, the pH, is your concentration of hydrogen when I rearrange my equation. So when I take a pH of 7, I go 10 to the power of my pH being 7. It's negative because there's a negative in front of my log. So for scientific notion, I go 1 times 10 to the negative 7. So I'm raising, to get my concentration, I'm raising 10 to the negative value of my pH. And that's how I get my hydrogen ion concentration. When it's nice, even round numbers like this. If I had a different pH would always be like that. When I have different hydrogen ion concentrations, sometimes you will get decimals in front of your 1. And that would be different. But for now, we'll just keep everything base 10, even numbers. All right, so look at it. If it has a concentration of 1 times 10 to the negative 4, what will my pH be? And it says right here, but how did you figure it out?
because you told us to figure it out right there.
Okay, so you raise it to the power of 10. It cancels the 10 out. You make it negative because it's a negative log. All right, so POH. Just like pH. So the only reason we use pH is because it's a nice, easy, round, positive number to work with, as opposed to these big negative numbers. That's the only reason we use pH. If I had to tell you that my hydrogen ion concentration was 2.3 times 10 to the negative 6, it just would be a pain. I would rather tell you my pH is 4.6. So the same way we measure pH by hydrogen ion concentration, we can measure POH by hydroxide ion concentration. This isn't talked about much because most of the time those two numbers stay in balance. pH goes up, POH goes down. So pH and POH will add up to 14. So water we say is neutral if it has a pH of 7. If that pH goes up to 8, then our pOH will go down to 6, because that's up to 14, right? If our pH is 1, our pOH will be 13. So the we'll jump ahead. Because water disassociates into hydrogen and water, the concentrations will always be proportional. If they're equal, they'll be 7. So this brings us to a concept called the dissociation constant. In water, our dissociation constant is 14, because the concentration of hydrogen times the concentration of water will be equal to 14. When you multiply exponents, you add them together. So if I have 1 times 10 to the negative 4 concentration times 1 times 10 to the negative 10 concentration, those, my exponents add together to equal 1 times 10 to the negative 14. My hydroxide concentration times my hydrogen concentration times my hydroxide concentration will multiply out to equal 14. And it'll always be the same in our aqueous water solution. Aqueous means water. This is different than our Ka and KOH. All right, so many reactions are, when I have an arrow, it denotes that it's one way, that my hydrochloric acid is going to completely dissociate. It's a strong acid, so that's true. But many reactions are not that way. So like water, it bounces back and forth. If you add more acid to it, you'll end up getting more acid, less base. So this is an example. This is our acetic acid. It is a weak acid. It does not go all the way. I was used to writing equilibrium symbols like this, but Microsoft doesn't seem to have that symbol, so I'm denoting it like this, and I think they're both right. But if I had a scientific software, it would look more like this, just so you know. So any weak acid will not just go one way. It won't completely dissociate. It is going to have some sort of balance between the reactants and the products. So it is denoted as Kw, which is our dissociation constant of water, which is always 14 because it's just the concentration of hydrogen and hydroxide multiplied together. Our dissociation constants of acids and bases are done differently. The water is just done that way because it's convention. It always equals 14. All right, I don't have a good number. So Ka and Kb will be the concentration of the acid times the concentration of its what we call a conjugate base. It is what it separates out into. So our acid, our base, that's all right. Our acid or base over whatever you started with, AH. I think that's, H is positive, that's negative. So unlike the Kw, they are expressed over your starting reactants. So it would be the concentration of product 1 times concentration of product 2 over how much is left undissociated, because it's not, the reaction doesn't go all the way. It stops somewhere in the middle depending on what it is. So if I start with 0.25 moles of hydrofluoric acid, it has a pH of 1.74. Find the concentration of hydrogen ions. All right, first step, can you find me the concentration of hydrogen ions based on that pH? So remember, negative log of hydrogen ions equals pH. So 10 to the pH equals your hydrogen ion concentration.
And so the log just becomes 10 in the equation.
The log is base, well, it is base 10.
Yeah.
Yes, it's always, if I don't write it, it's implied, it's base 10. So 10 to the power of your negative pH. Use your calculator, there's no, I mean, well. So you put in up. Did I do that right? So that should be your answer. Here's my pH. I raised 10 to the power of it. Because this is a strong, well, it's a weak acid. So hydrogen and fluoride are equally produced. So fluorine, what would fluorine's concentration be? It should be a strong acid. So they're equally produced. What will fluorine's concentration be? The exact same. It produces at a 1-to-1 ratio. So my concentration of hydrogen is 0.018. My concentration of fluorine is 0.018. I subtract both of those numbers. I subtract those numbers because it took the same number of atoms from the mass that we started with. Probably two. Think about that for a second. And it gave me that answer. Can you guys see if you can figure out that answer? Because it's taking away moles, not mass. And that should be a -3, not a subscript 3. All right, do you have questions? Should we dig into this a little more? So our dissociation constant, the concentration of our two products over the concentration of what's left of our reactant
Wait, so
in moles.
how do you know that like H and F are the same?
Because for every hydrogen fluoride that dissociates, you get one hydrogen, one fluoride. Because there's no coefficients in front of this.
But like, why are they the same? Both like point.
If it was a different atom, and let's use round number. If I had 100 hydrogen fluoride, even if it went all the way, it would produce 100 of one, 100 of two.
So it just has to be balanced.
Because it's balanced.
Okay. But what if it wasn't balanced?
Then it wouldn't be right. So you have to start with the balanced equation.
Okay.
But
like, okay. But like, what if it was like an ion? Like, because actually, never mind.
So even if it ionized, because it is an ion.
It is, yeah.
So you have to start from it being a balanced relationship, because, and that's the assumption you start from, is that your reaction is balanced. So, as I did over here, so my relationship here is denoted as, I have any acid. H is anything, any conjugate base and an acid. Or A is the conjugate base. H is the proton that dissociates. It goes into the two reactants that it disassociates to. So if I don't know what this is, and I find out my unknown liquid has a pH of 2.47, and I started off with a concentration of my material at 0.75 grams per mole. That's my reactant before it disassociates. Find me the Ka of this unknown liquid. So step one is going to be to find the concentration of hydrogen ions. How do I do that? Go. I need to see calculators in your hand. Knowing that my solution has a pH of 2.47, find me the concentration of hydrogen ions.
0.17 or 0.18.
So did you do 10 to the power of... It's possible I make mistakes.
I've got
Should we-
0.003.
Oh wait, no, I used
Wait.
0.003.
0.003. Oh, yes.
Yeah.
So change it into scientific notation.
Wait, good. 003 does that?
Yes.
Okay.
Otherwise, it's hard to... It's just hard for your eyes to see that many zeros. So if my hydrogen ion concentration is that, what will my conjugate base concentration be? Well, no, it's not going to add up to 14. This is not water. If it was water, that's true. It's going to be exactly the same because the acid and the conjugate base are in equal proportion because it's a balanced equation.
Wait, so what do we do with the 0.7 number?
0.74. So that is how much unknown acid I put into my solution to start with. You are going to have to find the concentration of that after this many moles
so this is
disassociates.
like the titration thing, right?
Yes, this
Okay,
is the
so-
titration.
Like if you were to explain like what was happening, like if we were actually doing this, you're like dropping the H thing into the A, right? And so are we finding the A before? Wait.
No. So this is not the titration. This is not the equivalency point. This is, I'm measuring the
But so
pH
what
of a
is
solution.
happening here? Like what? Like actually, like physically? what
I'm
is happening?
taking, I have my beaker. I put in 0.75 moles per liter of unknown acid. Right, so I have my liter, I add my
Okay.
0.75,
So
so it comes up to
the
a liter,
pH of
and then I
so
measure
what
the
is-
pH.
So that's the pH after. Okay. So okay.
So because I've lost 0.75 moles into this one and this one, I don't add them together, which kind of messes with you. Because you end up with 0.75 moles of this one, 0.75 moles of that one, or no, I'm sorry, not. You lose 0.339 times 10 to the negative 3 of each of these, but you only lose 0.339 of the acid that has disassociated. Even though you end up with two parts, they're two halves. You only lose that same amount from your undisassociated unknown molecule, HA. So how do you find, so if you know this is
So I did the
0.3,
same.
well, what's the HA? Yes, these two numbers are the same. They're both 0.339 times 10 to the negative 3. But what is HA? What is the
So-
concentration of the reactant before we started?
So we're multiplying that by 2 and then dividing it by the original like.
Yeah, so not this
Wait.
number. You have to subtract this from this.
Wait.
Because this much left the form of HA to become the hydrogen and the conjugate base.
Wait, so what are we finding? Like what is?
You're going to find Ka. So this is going to tell you
Which is Ka is how much acid, like the P.
how far the reaction has gone.
Can you explain that in different words?
So a strong base will completely disassociate, and you'll end up with,
Okay. So it's
so it's going to tell me how much of the how much product you got relative to how much original reactant you start with. So where this met reality was if you're working in production, because chemical engineering is all about making stuff, making detergent, we'll say. So I want to know how far my reaction is going to get, and then if I need to separate my product, because that's what I'm actually selling, I need to distill it. I need to know how much I'm getting because I know how efficient my product is. So pure scientists would have another purpose for it. I would only know how I'm going to make something from it because I would be an engineer. I want to know how much I'm going to make from this reactant. And maybe I want to make more acid than that. So I'm going to find something with a higher Ka because I want a higher efficiency. When we go to talk to buffers, if I'm in a natural environment and I have had a chemical acid spill and I have this acid, when am I actually going to be worried? Because everything is a cost balance. So if it is a real example, it is a septic tank who decides to not pay the dumping fee at the sewage treatment plant, instead goes and dumps it in the river, which human waste tends to be very acidic. So, and that's like not unusual. How bad is it? How long is that natural limestone going to take to buffer out that material? Or whatever, like, is it a karst creek that has a lot of natural buffer occurring and that it's going to be not catastrophic in a couple 100 feet, or is it closer to the coast where there's no buffering capacity and everything's going to be dead? How big a deal is it?
Can you solve that?
Yes.
Like,
all right, so my two
okay.
concentrations of both my acid and my conjugate base over my original reactant, subtracting what disassociated out. And again, I end up with this messy, tiny little number that I don't like, just like with the pH and the POH. Do I talk about this now? This is what I do talk about this now. So what I would want to do is just like with the acid concentrations and the hydroxide concentrations, I want to change that to a working number that I can use. So I convert it using my same negative log function. So I have this negative 3.39 times 10 to the negative 3. Because there's a decimal here, it's not a 1, we can't just knock off the tens, yes. So I have to use my calculator. Use your calculator and see if you can get that same answer.
Wait, can you go back a slide?
Yep.
Another one. Okay. I got 1.53.
I can't see anything. Okay, that's better.
Ben, can you make sure that's pointed roughly where it was?
Okay.
Oh, everyone's here, right? No, Lucas here. He was just like,
There you go. I didn't see you walk in.
we were all very concerned about you, Lucas.
Guys can find out.
Yeah. Alright, so I have my disassociation constant, my Ka. And by taking the negative log, I'm going to, this negative 3.39 times 10 to the negative 3 moles per liter, I'm going to convert that to a nice, easy number to talk about of 4.8. And that was a reaction that didn't go very far.
Wait, so what did you do with the... Oh, never mind.
So we then call that pKa. So just like our pH, our hydrogen concentration became pH, our hydroxide concentration became POH, our dissociation constant became pKa, or when we talk about base, Kb. Let me know.
Isn't it negative 4.8?
It's a negative
Oh, okay,
log.
it's a negative log. Okay.
Yep. Good catch though.
Wait, so couldn't you just take... So we had want to find. So couldn't we just use like an inverse log to get it from like
Yes.
take whatever like this number that we started with and just so we wouldn't even have to
Yes.
go through all.
Yes, you can use your inverse log function if you have that on your calculator. I think they call it an antilog sometimes. All right, as acid gets stronger, as the concentration goes up, the pH goes down. So our concentrations, concentration and P of whatever it is, POH, pKa, they are inversely related. One goes up, one goes down. All right, so next week, so your next chapter to read about is buffers. So I mentioned a natural system buffer. So do any of you guys have pools? No? All right. So like all this it hits reality when you have to manage the chemistry of your pool. So a buffer is simply something that resists change. So I mentioned the septic tank being dumped into the river because they didn't want to pay the tipping fee. And I think this isn't as much of a problem as it was 20 years ago because they really cracked down on that. So don't worry about that so much. But like in our area, we're mostly made out of limestone, which is a natural buffer. It can absorb high changes of acidity pretty readily. Pools are given stabilizers, so as people get in it, and let's be honest, our people are nasty. It can control it keeps the pH constant despite what people do in the pool, and then it can makes the other chemicals work faster. So a pH is just something that helps maintain a constant acidity despite what goes on. It absorbs the hydrogen or the hydroxide ion, and it's called the Henderson-Hasselbalch equation is what describes it. Okay. So I do not know if there's been any updates on our future here. Has anyone heard anything? All right. So I'm going to work under the assumption, worst case, that next week is our last week. So we have finished what is absolutely necessary for your chemistry concepts. So we're going to have our final exam next week. You have a copy of this exam. That is the exam I'm going to give you in class. So study it. We'll bring questions for the first half of class. We'll probably do some of those style problems, and then you'll take the exam the last 30 minutes.
For exam 5.
Exam 6. It's going to be both 5 and 6 together. That is a good question. So because I didn't want to spend time, because we are hustling it to condense this and moving double speed, don't go anywhere yet. I'm not done with you. And you're not singing. It'll be both 5 and 6. So it'll be long. So study both 5 and 6. If you can answer that, you will be golden. So your lab reports. I have not gotten to look through them. If you really want, let me know you want me to look through it. I want to show you a couple points for you to look at before.
Are they graded?
No, they're not graded. They've been sitting there. I am not going to be able to grade them and give them back to you. But a couple talking points that I saw sit. All right, so your introduction should include, at a minimum, a discussion of what conductivity is, what resistance is, what an electrolyte is, and why does electrolytes affect conductivity and resistance. I'd love to see you expand on that. Where do we find electrolyte solutions, like batteries and sports drinks? And what were we indirectly measuring by measuring the conductivity and resistance? It was electrolyte content. Why did we care about the electrolyte content? Because the body loses it when it is stress, sweats, exercises. All right, so then you should have a table. I love tables, which are well labeled. They're called Table 1, and then graphs are called figures, not charts, not diagrams. I mean, diagrams have their place, but they're called figures. You'll have your figures with your equation and your R squared. So this one, and probably a lot of your data, this was not great laboratory technique. Our multimeters were not designed to be used in liquid. So you are going to have faulty data. You're going to have a data point that's out here and isn't congruent. Own it. It's not great laboratory design. Like this was what the book said. I added the conductivity, but the more you use that conductivity sensor, the less well it worked. It wore out. Ideally, you would have made a new one with each. Yes. You what? What? Really? Like 2 minutes.
I already did that.
All right.
Yeah, we already know all this.
Yeah, I did something.
Because I
All right. Who is missing data? So you should just be having, when you're making this relationship between, this is your independent variable, your saline concentration, this is your dependent variable. Your measurements depended on this. You did not know what was in your sports drink. You couldn't say the more orangey it was, the more the conductivity went out. They were just not related. So you could only draw correlations between your known, the one you controlled, which was the saline solutions, and what you measured on those two things. So that gave you your relationship. You then could plot those relationships on a bar graph or any other. I saw other graph styles that were just as good. But that relationship could be plotted on what made the best. That's resistance. Someone showed a graph here, son. Yes, Kyle. Oh, Lucas.
I mean, when I was doing when I was trying to make like the scatter plot, it wouldn't let me do the equation.
Are you right-clicking on the trend line?
Yeah, and then I see like the option for it, but it's grayed out.
Yeah, I'd have to see it. Do you have your computer?
Not today.
Yeah. Yeah. All right. So in your conclusion, I would like in your both your discussion and your conclusion, I want you to say which one made the best sports drink and why. So it had this relationship. My conclusion was this was the best product. Okay. All right. So if you did all that, good. If you didn't do all that and you wanted to submit again, or who else was not here and does not have the data to work on? I know. Anyone else? Somebody else was not here that day. All right. Do you have your data?
Yeah, like the,
You got the data?
yeah.
Okay. All right. So it's just you. All right. So this was this is a pipette. So like what they showed you in the book, it had a stopcock here where you could measure how much was put in to get an equivalency point of when the pH. So a weak acid does not fully disassociate. You add, you titrate to see when it balances, and that's how you calculate how acidic, what potential acid could be in there. Like Leo was asking about the titration and the equivalency point. So this is an example of what it is. We do not have the glassware or the stands to do it, but I wanted you to see what it would look like. And it just has a scale from 0 to 1 to 9 as to how much would be added. Cool. All right. I'll see y'all next week for your exam and questions.